We discussed how to make alkenes largely through a reaction process that involved elimination. So we had something along the lines of a bromine, and then you treated it with a base, and then you ended up with an alkene, right? So that was your pretty much typical SN1, maybe SN2 chemistry, and that was how you created an alkene. We didn't really discuss, but you should have read the book and you would have seen that you could also do a reaction called a dehydration of an alcohol, right? And that involved addition of an acid. So if you have, like, say, HCl, the alcohol comes and it protonates itself. That generates a water or a hydronium ion. And basically what you end up with then is an elimination. Oops. Because this is now a wickedly good leaving group. It can depart, and you will end up with a carbocation, and then pretty much anything will deprotonate that proton right next to it, including that chloride anion, which will then go and collapse down into a double bond. All right. There are other ways of doing it. You can check your book as well for the generation of alkenes. If you have vicinal halides and toss in sodium iodide, you can then end up with, again, an alkene. Now, all of this is to say that you're generating alkenes on your way probably to something more interesting, and that is really what this lecture is about. And so I would encourage you to go refresh yourself on this reaction, which we discussed in lecture and is in the book pretty considerably. And then this is in the book, but it's pretty straightforward in basically taking an alcohol and turning it into a leaving group by making it into water. And then this is discussed in your book as well, and so you should go check that out. Now, what this discussion is mostly focused on is once you create your alkene, then what, right? Well, alkenes, of course, are very interesting molecules because they are extremely reactive. I mean, they're stable. You can put them in a bottle, you can put them in a gas tank, and you can light them on fire. But they're also very capable of doing really interesting chemistry. And I found this chart conveniently on the internet, and it actually has every reaction you need to know from the entire chapter, which is strikingly convenient. It is missing something very important. It is missing a discussion or really even a comprehension of regiochemistry and stereochemistry. So this will get you, I would say, 75% of the way there. But it's a really awesome chart to sit down and study. Even commit some of it to memorization. I'm not guaranteeing it's 100% correct. I did in fact find one mistake already on it, but it is, as a shorthand, going to be fairly easy for well, I would say it's fairly convenient, right? Now, before we hop into just doing all of these reactions and doing examples of all these reactions, it's probably good to point out that if you see a chart like this, you probably can assume there must be some sort of underlying mechanistic similarity between all these reaction processes, and you would be correct. If we consider the noble alkene, which we draw like this, that's just a double bond. And what's a double bond? Well, it's a bunch of electrons, to be honest, and a bunch of electrons and free electrons that share this way, and we can actually get rid of that double bond because now we're sort of sharing it this way. And these electrons, we have pretty much established, are more free to do chemistry than other sources of electrons, particularly electrons in the sp, or in these s-type orbitals. They're very committed to their nucleuses, whereas the pi electrons in the p orbitals are much more free to do as they wish. And so this risque behavior by them allows them to undergo a lot of interesting chemistry, and it's all thematically related to the fact that if you really think about it, an alkene is a nucleophile. And what are nucleophiles? Well, hopefully you know that by now, but they're essentially electron rich. They're electron rich things that attack stuff with their electrons. And that also means that they're possibly bases. And as it turns out, alkenes are bases. All right? So if you just remember that alkene is a nucleophile and that alkenes are bases, you will be able to do essentially all of these reactions. Now, you may miss some of the finer points, the stereochemistry, so the regiochemistry as to why, say for instance, in some of these cases, like with HBr and HCl and HI, the bromine ends up on the more substituted part, whereas HBr in the presence of a peroxide, it ends up on the less substituted position. Those things you're going to have to just watch the lecture and read the book for. But in general, if you just know this, alkene is a nucleophile, alkenes are bases, you'll be good. Now, are they better nucleophiles than bases? I don't know. They're pretty even. You know, they're good at taking protons. They're good at attacking electron deficient stuff. And so we're going to step through some instances in ways that kind of make that clear. Now, how they are nucleophiles and how they are bases is basically if you have let's just say an acid. So you got H and we're going to say Br, right? Now HBr, you are pretty aware, is an acid, right? In fact, in Gen Chem, you just say HCl, and HCl is just sort of crazy proton source. And if this alkene be a base, which it is, it's going to just come and deprotonate HBr. Or conversely, one could say it's going to just protonate the HBr. And you're going to end up, the HBr is going to protonate the alkene, which means that you're going to have something that will have now a proton associated with it, right? So it's going to have some sort of positive charge. I've drawn this fairly fictitious looking bond here because you're going to end up, when you do this, ultimately, a carbocation. So when you do deprotonate or when you do protonate an alkene, the question is, where does the proton go? Does it go here on the terminal carbon, or does it go here on the middle carbon, right? And so let's consider these two possibilities. One, we put the proton here, and then that gives us a carbocation in the, as we've thoroughly discussed, the more stable, thermodynamically more stable substituted carbon. If we put it on the middle, we end up with, again, as we have thoroughly discussed, the less stable primary carbocation. Okay, so in this particular process, when we do a protonation with an acid on an alkene, our intermediate is going to be this, right? And so that means that when you have an addition reaction with a halogen, because remember, you've protonated it and you've still got this Br minus, right? That's still now over here. The electrons are now all on the Br. So the Br minus is now going to go and attack that carbocation. And that's going to give you your first product, or the first product of our series, is the brominated alkene. And we can come up here to our stable, the figure rather, and look to see where our HBr is, to see if I've actually covered something like I said I would. And we've got HBr, HCl, and boom, it takes an alkene and it puts the halogen on the more substituted carbon, which means that this hydrogen, of course, that's still there, but now there's a second hydrogen there, and that came from the acid, right? And so that's exactly what happened. You have used an alkene essentially as a base. That base deprotonated an acid. The acid created a conjugate base. That conjugate base then added to the now created carbocation. And that is essentially the final product. Of course, this reaction is true for a bunch of different what I would say are mineral acids. And you usually find this with HCl. You can find it particularly with HI, and we already did HBr, and those will generate the corresponding haloalkanes. All right, in reasonably good yields. Now, what you'll notice, again, is that they are always on the more substituted positions. I could even add another carbon right here, and that would essentially ensure that I put my halogen on the more substituted position. And this process, this observation that the substitution reaction occurs on the carbon that is more substituted, is called a Markovnikov addition. And it is pretty much the rule for addition that follow the acid halogenation route. So in general, if you're going to go through something that's going to form a carbocation, that carbocation is going to be filled with it's going to end up on the most substituted carbon, just like we had said, and then whatever's in solution, the negative whatever, negative charge or what have you, is going to end up on that. And that's going to be your Markovnikov addition. All right, now can we fool the Markovnikov addition? Can we somehow get around the idea that it has to be substituted here? And yes, as a matter of fact, if I scroll up back to my little chart, I've shown this awful little beastie, an anti-Markovnikov addition, right? And this utilizes a peroxide and HBr. And what that does is that it actually generates a radical addition, okay? And that's kind of a funny, weird little reaction, right? So let's keep this in mind, ROOR, so it's basically some sort of peroxide, H2O2 or something along those lines. It can also be an organic peroxide, and then the HBr that we used before. Now how in the world, of course, does this create a radical, right? Well, hydrogen peroxide, if we draw its structure out like this, when you heat it, and we use the symbol triangle for heating, you actually do a homolytic bond cleavage that generates two hydroxyl radicals. And these are very potent radicals, right? And so these potent radicals then go find the most abstractable proton they can. And in solution, normally that's some sort of primary alkyl, right? We've done this. The primary hydrogen or the secondary hydrogen when you're using bromides, or primary, secondary when you're using chlorides, it pulls it off and it makes a very stable radical. Now, in this solution of hydrogen peroxide with HBr, all right, so we're going to throw in some, let's say, HBr, that's our reaction. We will first generate two equivalents of hydroxyl radical. Second step in this reaction, take the hydroxyl radical and HBr, and this is going to take the H off of the HBr. All right, and what that's going to do is then create a bromide radical. All right, and so you end up then with water, which is great, and then bromide radical, which is that's a picky radical, right? It's not like chloride. A picky radical, it'll go find something. It'll go find something nice. It's not a big rush, right? And so then you add in your alkene, all right? And your alkene, and then you've got your bromide radical in there. And the bromide radical now, it wants to be happy, just like anybody else. And so it's going to form a bond. Now, we had talked about bromide radicals, and radicals, all right, just like carbocations, want to be on the most substituted position. But this is a little different than what we had discussed in prior lectures, where the reaction was with an alkane. This is now an alkene, and there are actually available electrons in this pi system right here. So undoubtedly, it's just going to take one of those electrons and then toss one of those electrons in the most stable spot. And that would be on the center, on the most substituted product, which gives you this, all right? The anti-Markovnikov addition, because it's put your radical in a p orbital on your secondary position. And you'll remember, because we had discussed this ad nauseum, that radicals and carbocations are, of course, stabilized through both inductive effects as well as hyperconjugation effects by neighboring substituents, which means that radical is fine. The next step, of course, is that another molecule of HBr somewhere in solution will come in, and you'll get a recom, and you'll get a combination, and that radical, that organic radical, will then take that hydrogen, and it'll generate another bromide radical. And your final product will then be the anti-Markovnikov product. All right? So you can generate effectively both. Okay? In this particular situation, you've made the anti-Markovnikov product. And so in this way, now you've learned how to make this product and this product in this particular reaction sequence. Now, the next process is how you can make alcohols, all right? So alcohol formation can occur, just like you see up here, in two different stereochemistries, right? Or what you would call the Markovnikov product, where the alcohol appears on the more substituted carbon, and then the anti-Markovnikov looking product here, where the alcohol is on the less substituted carbon. All right, and so there are two approximate methods there to make this one that we will cover, and that is hydration, and then there's oxomercuration. All right, these two processes are somewhat similar in approach. Of course, there are multiple ways to get around to putting alcohols on double bonds. It's a very useful method for making alcohols. So we all know, in fact, it's maybe even worth revisiting this idea that you have an alcohol. I sort of briefly reviewed this, and you have OH, and then you throw in an acid. And it has to be a pretty strong acid, really. H2SO4, that's a pretty strong acid. That gives you an alkene, all right? And what I didn't talk about, maybe it was covered a bit in your book, but this is an equilibrium, all right? This process can go backwards and forwards. And what you can end up with is a reverse happening, where you have an alkene, of course, and then you have hydration. So you have water, all right? And then that double bond goes in it. Let me actually just produce something that looks a bit like that. And so that can just pull off that hydrogen right there, right? And so in that process, you're doing a deprotonation, so that means you're going to end up with a carbocation in the more substituted position, and then your hydrogen here. And of course, when that happens, you've made some transient amount of hydroxide, and that hydroxide is extraordinarily short-lived, but it's there and it can come in because it's going to quench that carbocation, and then that gives you your alcohol. All right, and so that process is also facilitated in the presence of acid. So it stands to reason that when you have something that is, say, more substituted, something that looks like this, for instance, with a methyl group here and a double bond, you can imagine that in the presence of water, and then you throw in a wee bit of acid just to make sure you've got extra proton, right? This is acid catalyzed. Remember, you will end up with the Markovnikov product. All right. Now, let's say you did this reaction. It is a very stubborn, the first step of this is just taking a proton. I even did it on water. This really truly does have to have, a little bit of acid in it. You throw an HCl here just to add a little bit of oomph to your acid because the alkenes, they're bases. They're not great bases though. So sometimes acid's not enough. If acid's not enough, it's just mineral acids are not enough. You can turbo boost this reaction in something called an oxomercuration. And in a common reagent, you definitely don't want to drink, no matter how thirsty or bored you may be, is this. So we put a little mercury right there, and we get that right there. All right, and this actually is in an equilibrium as a salt with this. All right, and that funny little reagent right there is really, really what you'd say it's a Lewis acid, right? It's a metal, it's positively charged, and it is basically ready to go. So if you have an alkene right nearby, so say for instance something like that, and you have your mercuric reagent, and that is just super ready to go, that alkene is just going to be like, wow, a positively charged mercury. That is exciting. And it's going to form a, well, mercury, let's be obvious, let's be clear. Mercury is no proton, right? Mercury is a big atom. It's a big metal, all right? It's a big soft metal at that. Lots of nice squishy soft protons. So it actually does something a little bit different from a proton. It really does straddle the double bond. All right, so you create this what's called a mercurinium ion, and that mercurinium ion can basically it's this, all right, and that happens because mercury and other big atoms, I guess protons will do this too sometimes, you'll see this, but let's just say for now that big atoms will form this bridged cationic structure. And that makes the double bond pretty reactive, right? Because now you've got this huge atom straddling two carbons, and it is basically ready to be attacked. So up here, what did we attack with? We just attacked with water, and that's fine. We just had a little bit of acid to a solution of water. And so what would happen if this were also in water? All right, so if we added a little bit of a little H2O to here, what we would find is that even with the even with that proton, it's not even have to be deprotonated. You will end up with an attack just to get that mercury, maybe onto just one carbon. Now, where do you suppose this water is going to attack? Right, this water can attack here, or this water can attack here, and it turns out it's going to end up attacking at the most substituted carbon. All right, and it attacks preferentially the more substituted carbon because it produces that bond right there is a bit more positively charged, right? And the reason is because well, let's call it. In fact, let me just write this name of this little weird thing down. The mercurinium ion. Actually, it's a bit stronger here. Just like up here, we draw the hydrogen on this side of it, and the carbocation here. The mercurinium ion does straddle the pi bond, but it's a the big covalent bond, the strongest covalent bond, is actually at the terminal one, which makes sense because this is going to have a partial positive charge, and for the reasons we have discussed so extensively, it's better to have a partial positive charge on a secondary carbon. So anything that's going to attack is going to provide you with the Markovnikov product. And what you're going to end up with then, after this reaction, so that goes and forms this and this intermediate, and then the water attacks, and then you end up with something that looks like this, an OH, and then the mercury comes down here. All right, and you have an organic mercury product, right? And that's not actually what you want, right? You want the alkane. And so how do you get the mercury off? Well, it's actually not terribly difficult. You simply reduce it off with sodium borohydride, and you get your alcohol. Okay, and well, now hold on. You may say, that's where'd that hide? What? Right? So if you look here, there's a proton here and a hydrogen here. There's two hydrogens here, but over here you got 1, 2, 3 hydrogens. So where did that extra H come from? And the answer is actually this. So sodium borohydride is a source of H minus. And you don't see H minus very much, but that's what it provides, is H minus. And so what substitutes, or what essentially pops off the mercury, is an attack H minus, facilitated by boron. And we'll get more into sodium borohydride as an anhydride source. It's actually a really interesting source, but essentially you have boron, and it's got hydrogen, hydrogen, hydrogen. And boron normally only likes to have 3 bonds, right? This is a stable boron complex. When it has a 4th bond, remember, boron becomes negatively charged. It's sort of like anti-nitrogen, where nitrogen becomes a cation when it's got 4 carbons. It becomes an ammonium. Boron becomes negatively charged, all right? And boron wants to get rid of its negative charge, and it's quite happy to throw that negative charge kind of on the hydride right here, and so it'll just push it right here. And then it's like, you know what? Hey, check out that thing over. That's weird. Go get it. And it's like, and essentially that's how you end up with hydride over on the other side. All right, so that's pretty convenient. There's also a kind of another interesting thing that I've drawn up here, and I didn't really point it out, but you kind of got to think of it. This is a huge atom, right? So I've purposefully drawn it sort of in the back, and this water attacking from this side. Water can't attack from the same, nothing can really attack from the same side as the mercury, all right? So in addition to being regiospecific, all right, so the regiochemistry being that it prefers this region of the molecule, that secondary position, it's also stereospecific in the sense that water will attack from the opposite face of the mercury, all right? And so you will end up with specific stereochemistry that you normally don't get in the mineral acids because the proton is tiny. It really doesn't induce any sort of stereochemistry. It does induce regiochemistry, as we had shown before. It's regiospecific, where you end up basically always getting the Markovnikov product or the anti-Markovnikov product. That is regiospecific. But not so much stereospecific, right? These aren't even stereo. You can't even form stereoisomers on those anyway. Now, in mercury, you can end up with the anti-addition to the double bond, right? And so how does that work? So if you have, let's just do this mercury addition on a cis double bond. All right. So you got a mercury addition, and in fact, let's draw this so that the double bond is coming out, so that the methyl groups are coming out towards you, right here. And methyl groups are coming out towards you, and then there's a hydrogen back here. There's a hydrogen back here, and I think it probably helps some people to realize that the reaction of an alkene occurs on largely the face, especially if you've got a great big atom like mercury. And I realize now mercury should be silver and not orange. Double bonds are orange. So if you've got some great big ion like mercury, what you're actually doing in these reactions is the mercury is going to come and it can sort of just attack from the top, right? And so you start to form a bond like that, all right? And that creates something that looks more like this, right? You end up with a bond here, and then that thing comes down here, and that's your methyl. I shouldn't be very specific. That's methyl. That's a methyl there, and then that's your methyl coming down here. And then behind you, there's your H, and there's your H. And you then have an orangey bond for your mercurium ion, right? Okay, and then these are in the plane of the screen right here. And what you then do for how water attacks, right? So if you're water, you're going to be like, all right, I'm water. I am ready to do some attacking. But you're like, what? There's a mercury right there. Nah, I'm going to go instead. I'm just going to go this. I'm going to go like that. And of course, this is a symmetric molecule. So you're like, whatever. I'm going to go over here. It doesn't make any difference, right? What you end up doing is always, in this particular case, reacting on the opposite side of the mercury. So that means that your final product now has something that goes down like this. This methyl group's still down here. That hydrogen is still over here. And your mercury is now kind of pointing up, still in the plane of the paper, but, like so. And now these little fellas right there, those are now kind of gone, they're not going to pop up, right? And then that one's going to pop up. And let's give this water a different color, just so we're clear. Doop, 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 doop. And that water is going to come right, and that water is going to come down from here. Oh. All right, and so that's where your alcohol is going to add. And so your alcohol is now anti to the mercury on the double bond. All right, and so you can end up with very specific stereoselectivity. So let's write that down. Okay. Now, in both of these cases, essentially your reactions, and let's go scroll up here. We had mentioned sodium borohydride and oxymercuration, but you'll notice there's a borohydride, there's BH3 actually, it's not sodium borohydride. BH3 actually promotes this anti-Markovnikov. Now boron is just, it's a very interesting reagent. It's because it's so unlike most of the things that we've covered before, and that comes from its fact that it's on the left side of carbon, and it tends to be negatively charged. So if we just play with boron for just a second, right? Not even charged boron. So we're going to say, we're going to do something called a etherate, a boron etherate, right? So what is BH3? So normally you think you buy like BH3, but you can't buy BH3 because boron, you need to remember, is going to be has an empty pi orbital. And nature abhors a vacuum, so anything you throw in that is going to get stuck. So usually what they do is they actually sell it as an etherate, right? And so something is stuck in that orbital. Usually tetrahydrofuran is going to be jammed up in there, and that's fine. The lone pairs satisfy boron, and essentially that you'll often see the reagent actually called BH3 THF or some sort of etherate complex like that. But that's fine. It's all the same. The reactive component, the reactant constituent, is BH3. Because boron loves electrons, if you have an alkene, it would be quite happy to get rid of that THF and just go whoop, bonk, right? And boom. What you then end up with is, instead of an alkene, you'll end up with a borate. And a carbocation right there. So, that's pretty neat. Now, you'll notice that I have drawn a BH3. And what did I say about BH3s up here? Well, I'm sorry, BH3 minus. And what did I say about BHs with minuses? They love to dump their hydrides. So let me actually re-illustrate something along these lines, right? So yes, boron has hydrides coming off here. That would make boron negatively charged. Boron shoves its hydrogen, its negative charge, onto this hydride. That hydride says see you later and goes over to the carbocation. Everybody wins when that happens, because now you end up with a neutral molecule, BH2, and the hydride has now moved over to its new home. And once again, you end up with the borane actually sort of the substitution in the anti-Markovnikov position, right? Well, and what can you do with that? Turns out there's plenty of stuff you can do with that. That borane is once again fairly easy to remove in the presence of the right conditions. That if you throw in hydrogen peroxide and a little bit of base, you will end up with this, what we've been calling an anti-Markovnikov, oops, that's a hydride, I'll just redraw that, anti-Markovnikov addition there to your alkene. And that, once again, is consistent with this. So this chart, hooray, did not donk up that one. So that's good. All right. Boranes can also actually do the same thing, generate the anti-Markovnikov product, if you, instead of throwing in the sodium hydroxide and hydrogen peroxide, if you instead threw in Br2, for instance, what you would end up with instead is your anti-Markovnikov product, but with bromine in its place. And of course that hydride here as well. So you can also end up with a hydroboration product in the anti-Markovnikov position. Now, again, there is some obvious regiochemistry here, but there is actually some very interesting stereochemistry here as well. We go back up here. I've drawn this little guy, this little weird thing right here, where the boron is just like, here, have a hydride, right? And you notice that that's all happening within a 1, 2, 3, 4 carbon little transition state, so an intermediate. So That's going to have to be pretty fast, right? So it turns out that boron likes to add its hydride to the exact same side of the double bond that it is on. So if we were to go down and discuss the stereochemistry of this reaction, specifically we were to draw a six-membered ring, and we were to throw H3 ether 8 at it, we would end up with this, where the methyl groups now point down, and you end up with BH2 and your hydride that came from here, from your H, on the same side. So what is the actual, what would be a better way to illustrate this mechanistically, I guess, than what I've illustrated up here? There's nothing wrong with what I've drawn up here. You'll see this oftentimes done in textbooks, but maybe there's something a little bit better about how you can imagine that in this particular reaction with boron, instead of pretending that you have a flat surface, let's go into 3 dimensions again. And remember that the pi system exists above and below the plane, and that boron, I don't know, boron's usually blue, isn't it? Has a hydride over here, and then a hydride over here, and then a hydride over here. All right, and so, or an H and an H and an H. Now, what you have, of course, is this electron system. These electrons that are over here, and these electrons can just attack boron. And as it's starting to form its negative charge, right, and this is starting to become partially positive, and that's starting to become partially negative, what the hydride can do, because it's also very fast and in such a very tiny transition state, it can then do this stepwise but very fast cyclization. And what maybe you might draw as a let's say a transition state here in this boron process would look something more similar to a 4-membered ring forming, where you have an orange, okay, and then boron is right here, and you have that it's coming as a hydride right here, right? And so that this little box thing here means that essentially whenever you do this reaction, the borohydride addition is going to be, or the hydride addition is going to be on the same exact face of the double bond, okay? And so you always end up with something that looks like that, where the boron and its accompanying hydride is on the same spot. It turns out that the process of removing the boron with sodium hydroxide and peroxide does a great job at keeping everything. Let's just move this over just a touch. On the same face as well. So what you see is that you'll have, we'll just throw in H2O2, sodium OH, and that means that your final product is an OH here, and your hydride is here. And this started off with 2 methyl groups, so actually you have made a chiral center right here, and 2 chiral centers as a matter of fact, and you've done it stereo specifically. Now, of course, the addition could have come from the top or the bottom, but the point is that no matter what you do, this reaction will always create a product where the 2 methyl groups are on the same side and the alcohol and the added hydride are on the same side. Now compare that, these 2 reactions that we just discussed, all right? Where if I were to give you this product and say what I'm looking for from you is I'm looking for a way to make the alcohol with an anti-addition, right? So an anti-addition, as in the alcohol is going to end up being on the opposite side of the added alcohol, of the hydride, right? Or I'm looking for a syn addition. And in a syn addition, what I'm looking for it to do is to put the alcohol the other side along with this proton, right? And these two methods are very different. One is a Markovnikov process, and one is the anti-Markovnikov process. Do you remember what the reagents were to get there? On the top, you threw in, this is an oxomercuration in water, followed by removal with sodium borohydride. And on the bottom, this is just borane addition with peroxide and sodium hydroxide to displace that. And in these two processes, you get different regiochemistry and different stereochemistry. So you end up with different products.